Okay, folks, good afternoon. Just an announcement that quiz 1, quiz 2, and homework assignment number 1 are graded. I think if you log into Blackboard, you should be able to see your own grade. If you cannot see your own grade, let me know. I probably have to turn something on or something like that. If you are curious how come the first column is quiz number 2, and then the second column is quiz number 1, and the third column is homework number 1, is that grading system in Blackboard. I assume that you can actually switch the columns or actually rename or relabel a column. Apparently you cannot. So first I graded your second quiz and put the grades there. That's why that's how it appears. So homework number 3 was kind of extended. The deadline was extended to right now. So if you have homework number 3, please submit it. If you are a distance student, please email it to me before the class ends. What we have been doing so far was first we developed some transfer functions that predict the small signal behavior of DC-DC converters. We had a table. Also, this homework assignment that you had was focused, for instance, on the buck-boost converter. Then we looked at the control perspective. How is it that we want to control a DC-DC converter? We measure the output voltage, we compare it with the reference, then apply that error to a compensation network that we are going to design today. Hopefully, we will get to design it. And then there is a modulation block, and then it's the duty cycle and the rest of the system. So what we talked about last time was, if you look at our loop gain, the yellow, the green basically circle over here, what are the basic characteristics that we expect from our loop gain? For instance, our loop gain should be very large at frequencies where we have a dominating undesired harmonics, for instance, in the input voltage. Like, for instance, you are trying to rectify the power from the outlet. There's 120 hertz ripple in that, and then you're feeding that to a DC-DC converter. So you have a significant 120 hertz harmonic in your input voltage. So you want your loop gain to be large in those frequencies. The other expectation is our loop gain should have a very wide or high bandwidth, meaning that the system should be fast as it could be. We are always trying to make our system fast in case there is a sudden disturbance appearing in the system. The system can recover itself in a shorter, time. And also, the very basic expectation that we have from our loop gain is to guarantee or make sure that it is actually stable. How do we measure or quantify stability? We look at the phase margin. If the phase margin is positive, the system is stable. In order to be really, really sure and the system be deep into stability, we sometimes say the phase margin should be more than 30 degrees or 45 degrees or 60 degrees or something like that. If you are curious about what phase margin is, we look at the Bode plots of our loop gain, the magnitude and angle. The crossover frequency is defined when the magnitude is 1 or 0 dBs. And then the phase margin is how high you are with respect to the line negative 180 degrees. So phase margin is technically defined as look at your phase angle at the crossover frequency, then add 180 degrees to it. If it is positive, you're stable, you're doing good. All right, so this is what we expect from our loop gain. So today we are going to actually look at this loop gain and see what the components that we have in this loop gain and how is it that we can design a compensation network. All right, so our loop gain is for instance, we are trying to control a DC-DC converter, most likely a buck converter. So our loop gain is we measure the output voltage. So there's a sensing network involved. Then there's a negative sign there in the loop gain. We never consider that negative sign. Then there is a compensation network involved that we don't know about yet. Then there is a modulating block. And then the converter itself has a transfer function of control to output transfer function. Okay. All right. So let's look at all these little components. We are already familiar with GVD, where we were analyzing our converters. So for instance, let's take a look at a sensing network of H of S. So presume we have a DC to DC converter. Obviously, we have a load. For instance, here it's a resistive load. The easiest way of measuring the output voltage is just using resistors, using a resistive divider. Okay, it's important to make sure that if you are having a common ground, that your load is a ground and your controller has the same ground, just make sure these grounds are not messed up. Some of them are not floated. So hypothetically say you have a controller that works with, for instance, 5 volts, but your output voltage is like 100 volts. You cannot directly connect 100 volts to your controller, or for instance, you have a DSP and it has like an analog to digital converter. The input of an analog to digital converter can go as high as 3 volts. You cannot directly connect your 100 volts output there. So one cheap and simple way is just use 2 resistors to just basically divide the output voltage or scale it down to something that is palatable for the controller. Or you can make it a little bit fancier and buy a voltage, transducer or something like that. Resistors are very cheap. Voltage transducers are obviously a little bit more expensive. If you do it like this, assuming that this current is almost 0, in other words, your controller is not really loading your current, your resistive divider. The gain of your sensing network is only R2 over R1 plus R2. Okay, it's quite simple. All you have to make sure is R1 and R2 are large compared to your real load. Okay, we have a real load over here that is consuming power, but you don't want R1 or R2 actually consuming any power. First of all, because they are going to get hot and dissipate power. The other one is the efficiency is going to go down. All right. So you got to make sure that R1 plus R2 is much larger than your real load. Okay, otherwise they appear to be to a load basically to the system. For instance, if your load is 10 ohms, maybe R1 and R2 could be maybe 100 times 1,000 times more than 10 ohms, like 10 kilo ohms is good. Don't go very excessive in terms of selecting R1 and R2. For instance, 10 mega ohms from this perspective is very good because it's much larger than your load, but the larger your resistors get, you're going to be more sensitive to noise. So if there is a little bit of a noise induced over there, it's going to actually feed your controller. So it starts acting like an antenna that collects noise for your controller. So make sure R1 and R2 are large, like 100 times larger than the minimum value or maximum value of your load, but not in the mega ohm, scale. The other thing is how to adjust R1 and R2. All you got to make sure is this is equal to Vref over Vout. Okay. Your controller is pretty much a chip. It's something that you can purchase. And these chips have internally some reference voltage that is thermally compensated, and it's a number, like for instance 3.5 or sometimes 5, sometimes 4, sometimes 2 point something. It depends on the technology that they have used to create that thermally stable reference voltage. So Vref is dependent on the chip that you purchase. Okay, it's like 2 volts, for instance. And you would like your output voltage to be 100 volts. So that means you're looking at a scaling down of 50 times. So Vref over Vout determines R2 over R1. You have an extra degree of freedom, which one to choose what. All right, so this was all about the sensing network. Quite simple, just the resistive divider. The modulating block, we talked about it last time as well. There are many different ways of converting the level of a signal to the width of a pulsating signal. So technically, I have the compensation block. Then we have an analog signal over here, very smooth, like the output of an integrator. It goes up and down very, very smoothly. We call it the control signal, or VC. Then we have a PWM block. Oh, let's not call it, let's call it PWM. And then it goes to the gate, or sometimes the gate driver. Okay. So there are many ways of converting basically this smooth signal to a pulsating signal. Okay. And it's kind of a digital, process. So you're looking at a signal that is going up and down continuously to the output that is kind of a little bit discrete, basically. So one method, as we discussed previously, is intersective. Which is the most common approach. So basically the idea is create a sawtooth waveform and this is VC coming from your compensation network, and then just compare them against each other. Okay, something like this. It's a very, very simple. This is just a comparator. Okay. I think we had this diagram before. Let's take a look at it one more time. So the sawtooth waveform is fixed frequency. Which is your switching frequency, basically. So if you are trying to switch your converters, switch at 100 kilohertz, this sawtooth waveform should be at 100, kilohertz. So basically, the chips that you purchase, you have to on the outside of the chip, you have to connect a resistor and a capacitor to create this sawtooth waveform. And there are tables or graphs on the data sheet of the chip, which tells you, if, for instance, if you are looking at 100 kilohertz, your capacitor should be this much, your resistor should be this much. So you can actually have an understanding about it. One thing that to highlight over here that we did not mention is the peak value of this sawtooth waveform becomes important. I just call it V sub M, M standing for modulator or modulating. All right? And then we have VC kind of being compared with it. So whenever these two lines or curves cross each other, that's a decision-making point for me. Well, this is an exaggeration. In reality, VC doesn't change this quickly. I'm just trying to demonstrate it. Okay. Okay, so this is the output of your PWM signal. PWM block. Okay. So if you think about it, there is a little bit of a digitalization happening over here, meaning that once your VC crosses this ramp at this particular point, it doesn't really matter how VC changes until this next crossing point. So for instance, VC could go like this. Or it could go like this. It doesn't matter. We kind of take a sample of VC at that point. Then when they cross each other again, that's our new sample. So we are kind of discretizing the update rate of our duty cycle. VC has all the information about the duty cycle, and it's a continuous signal. But then on the output of the PWM block, we have a signal that is kind of sampling that, and our update rate is only once every cycle. So if you open up some papers or some dissertations back in the 80s, they were trying to model this behavior of kind of a sample and hold behavior, and it actually naturally adds some delay or sometimes a stability challenges to your converter because you're only updating your duty cycle once every period. But we don't want to get into those details. All we care about now is find out the transfer function of this simple modulating block. All right, so I'm just going to do a small signal model. So first, remember when we do a small signal modeling, first we do a DC analysis or steady state analysis. So technically, if my control signal is as high as Vm, remember Vm is here, the peak value of my triangular waveform, okay, that is Vm. Then my duty cycle is always going to be 1. That means I'm keeping the switch on the entire time, the entire duration of the period. If my control signal is 0, then the duty cycle is 0. All right? So you can kind of get a feel about under a steady state condition, or actually look at this, this triangle and try to actually do some math, you're going to realize that this is the gain of the block. Okay, remember this is an average model. The output of the PWM block is not a continuous signal, but on average it represents the duty cycle. So if I increase or double the size of VC, the duty cycle is going to get doubled, assuming that you are still having an intersection. So this is basically a very simple model for our DC model for our PWM block. If you want to make it a little bit fancier, but this class is not concerned about this, your more accurate model should look like this. And then you have like a sample and hold here with a sampling rate of the frequency, and then this is going to the gate. But, I mean, we are trying to keep it simple here. All right. So my very simple DC model is duty cycle is VC over Vm. Okay. Question?
What's the set point for Vm, like the top?
Well, it depends on the chip that you purchase. It's sometimes 5 volts, sometimes a little bit less than 5 volts. Remember, they generate this sawtooth waveform by charging and discharging a capacitor. So the higher this voltage is, the more losses you're going to have in this standard capacitor. But at the same time, the higher this voltage is, a better resolution you're going to get. But since your controller operates, for instance, with 5 volts, usually it ramps from 0 to 5 and then resets to 0 and then 5, or 3.3 or 4 or something like that. So it's usually less than 5.
So VC would be the scale down value.
Exactly. So VC is going to automatically scale down itself. Okay, that's a great point. And sometimes if you have a very sudden change, your VC may get to 10 volts, meaning that duty cycle of 100% is not enough for me. I need 200% duty cycle, which is impossible. Even if you keep the switch on all the time, you can only achieve a 100% duty cycle. So sometimes our control signal may get out of the range of 0 and 5. It may get to 7. It may get to -5. And there are like anti-winding actually blocks in your system. If you have to actually add them to the system, make sure VC never goes beyond 0 and 5. Otherwise, you're pushing your converter to do something for you that it cannot do, basically. Like having a negative duty cycle, it's impossible. Or having a duty cycle more than 100% is impossible. Now that we are done with the DC model, let's look at the perturbation. Okay, so I'm going to perturb my control signal. It has a DC signal, DC value of VC plus some small signal perturbations. And that would result in a duty cycle that is having a DC value and some perturbations. Okay, so I'm just going to plug this into my average model. And Vm is constant, it never gets perturbed. So this was a time domain analysis. It doesn't matter, everything is constant. In the frequency domain analysis, it's the same. So the transfer function that I'm trying to find is just 1 over Vm. Okay, so if Vm is 5, it's like 0.2 basically. So as I said, if you want to make it fancier, in some papers the transfer function is actually a bit more complicated because of that sample and hold effect in the system. All right, so this is how it is done most of the times, 99% of the times. But in case you are curious, so they came up with this idea back in the, for instance, 70s. If you are curious if it is possible to do it in other ways, the answer is yes. To give you an example, instead of doing an intersection-based kind of a PWM, we can do a delta sigma modulation, basically. All right. The way this one works is obviously VC, the control signal, is the input to the system. And you subtract it from the duty cycle signal that is applied to the gate. Okay? So this is a kind of a smooth signal. This is like a pulsating signal. All right? And then you look at the difference between them and integrate that difference. When it reaches a certain threshold, then you basically like a quantizer over here. Then you kind of flip. Okay. So this acts like a quantizer. So if your error is below a number, you don't do anything. But if, for instance, it passes 0.5, that means on average, your duty cycle and VC are getting way far from each other, so you actually turn the switch on or off, or accordingly you do something. And once you do that, that average is going to go to a negative territories until the next thing arrives. Sometimes instead of using this comparator, they use a kind of a hysteresis kind of a thing. To avoid jittering, you actually have a hysteresis thing. And as you can see, this is not a fixed frequency thing. We don't really apply the frequency over here. Whenever this error gets beyond a certain point, you turn your switch, for instance, on or off, something like that. In order to achieve a fixed frequency, you can actually place a sample and hold block over here too. Okay, so this is a sample and hold. All right. So we use sample and hold. That means that the input is going up and down just randomly. The output is looking at the input every, I don't know, 100 milliseconds. For instance, if you're switching frequencies 10 kilohertz or something like that. So there are papers actually looking into this. Is it more effective than the PWM scheme? There are some inverters that operate based on this. So you don't have a fixed frequency or a PWM signal. You just look at your pulsating signal that is applied to the gate versus versus your compensation, signal. So assuming that this is between 0 and 1, these levels are also 0 and 1. All right. And there might be some other methods. For instance, we have a lot of digital methods that, we are not going to analyze over here. So let me just. So we have a question?
Yeah. Does the quantizer limit the limit for the integration output
Oh, that's a good point. Sometimes you may want to actually add a limit over here as well, because for instance, the quantizer is doing the best that they can, but the error is still growing up, but you don't want to integrate extra amount of error. So sometimes, yes, there might be a limitation over here as well. MATLAB usually shows us with this. All right. So we looked at the sensing network. We looked at the modulation block in a simple design. These are just simple gains. They are constant values. So now let's look at our loop gain one more time. This is my sensing network, or H of S. Compensation network transfer function. The PWM modulator. Most of the times we use a PWM modulator. For the delta sigma modulation scheme, it's really hard to come up with a simple transfer function. And then, oops, these are not additions, these are multiplications. And then, for instance, I am looking at the Bode topology. So this is the control to output transfer function of that topology. All right, and omega naught is all right. So our objective is to see what this guy should look like. So this is for the Bode. So this is H of S. This is GM. All right. So now I'm going to switch to kind of a simulation, so you guys and kind of a math-get comparison, so you guys can actually see if we put a bunch of suggestions over here, how they are going to achieve our goal. Okay, so I'm going to switch to my my office computer over here. Any questions so far? Okay. I have already uploaded these files on Blackboard. What you see on the screen does not look like the buck converter, but it is a buck converter. So basically, this portion is you know, how the inductor and the capacitor are doing the integration things that they are doing. This blue box over here is the input voltage, and I can select to feed a constant voltage as my input voltage, or like an input voltage that jumps from one number to the other, or like an input voltage that has like sinusoidal perturbations on it. This blue box over here is my load, and I'm doing the exact same things to my load as well. Like my load could be a constant of 5. Let me zoom in a little bit. Zoom in. Okay. And then down here, I have a bunch of suggestions as my compensation network. So this is implementing my G of C, my compensation transfer function. And this down over here is my PWM block. So I try to make it as close as possible. If you purchase a chip, basically they have a constant current. They integrate that constant current. Then they reset that capacitor, and then compare it with the duty cycle signal, and then the rest is like your gate driver or something like that. Okay. If you are curious about what is happening in the end, this block over here is my basically comparator. These two are a comparator. But in MATLAB, when you compare a signal, the output is either 1 or -1. It is not 0 and 1. It is 1 and -1. In order to change it to 1 and 0, I add that signal with 1 and then divide it by 2. So I just shift it up and then divide it by 2. So I'm all jumping from 0 and 1. 0 means the switch is off. 1 means the switch is on. All right. So I have some candidates over here in terms of some suggestions. If we try to have a blind design, just put a bunch of transfer functions over here and see how they operate. Now, before that, let's assume my duty cycle is constant. It's oh, by the way, why is that everything is multiplied by 5? Because my sawtooth waveform over here goes from 0 to 5. In other words, Vm is 5. So this block over here has a gain of 1 over 5. In order to cancel out that gain, I am actually multiplying my duty cycle by 5. Okay. So this top block over here is saying my duty cycle is just a constant of 25%, but I have to multiply it by 5 because the downstream block is dividing it by 5. All right. As long as the measurement of the output voltage is concerned, this is my output voltage. I just have a simple gain of, for instance, my output voltage is supposed to be 12. My reference that is applied or is available to me from the chip that I have purchased is a weird number of 2.45. I've intentionally put this weird number over here. So you're looking at a very simple gain of 2.45 divided by 12. All right. And we compare them against each other, and the rest is the compensation network. So first, I'm going to run this like in an open loop fashion. I'm assuming that duty cycle is 25%. And you can actually observe some of these transfer function behaviors that we were discussing. First thing that I'm going to do is I'm going to keep the load constant at 5 ohms. And I am going to first, let's run it with a normal situation. Like input voltage is 48. Duty cycle is 25%. So the output voltage is supposed to be 12. So let's do it. And it is 12. All right, the trace down here is my output voltage. You can see it is being regulated around 12, and obviously there is a little bit of a ripple on it. This is the switching ripple that you can predict or calculate. Depends on the value of the capacitor, the output capacitor. Okay, so this is the normal operation. Now keep this in mind and compare it with the case that I am actually perturbing my input voltage. So my input voltage has a DC value of 48, like the previous case. But in addition to that, I have some 100 hertz fluctuations or perturbations added to my 48 volts with an amplitude of 4. Okay? So now let's see how my output voltage looks like. Well, obviously, this is an open loop behavior. The input voltage is perturbing, but the duty cycle is still constant at 25%. So technically, I'm multiplying the input voltage by 25%, and that appears in my output voltage. So you can see my output voltage has a ripple. The average value is still 12. So the average model still predicts that your output voltage should be 12, and it is 12 on average. But then it fluctuates with a peak of 1 volt. The input was fluctuating with a peak of 4 volts, multiplied by 25%, 1 volt. So that transfer function DC value gains are actually holding over here. This is not very hard to imagine, because in the buck converter we know that V out is D times Vn. So if I perturb my Vn, it will be multiplied by D and appears as perturbation in my output voltage. That's very, very simple to imagine. Now, something that is not simple to imagine is, okay, before I do that, let me also show you what happens if I have a step change in my input voltage. All of a sudden, for instance, my input voltage jumps from 45 to 45 plus 6 at 20 milliseconds, something like that. Just randomly jumps up. All right, now let's take a look. All right, as you can see, because this is an open loop behavior, my output voltage also jumps from 25% of 45 to 25% of 45 plus 6, okay? It doesn't know that it has to remain at 12. Okay. So this is an open loop behavior, and as you can see, there is also a kind of a transition going on. So before I was under a steady state condition, V out was duty cycle times Vn. After I reached a steady state condition, again, V out is duty cycle times Vn. But in between, you can see there's a transition going on. And we would like this transition to be at least as fast as possible. All right. So this was all about changing the input voltage. What about the load? So now, instead of having a constant, so I'm not changing the input voltage anymore, just set it at 48. And instead, I am actually changing my load resistance. Let's say for a weird reason, my load on average is 5 ohms, but with a frequency of 100 hertz, it's actually fluctuating between 4.5 and 5.5 with an amplitude of half an ohm. All right, now let's take a look. So remember, this model, the simple average model, does not predict what happens in the system when the load changes, because there is no R in that last equation that I have on the screen. But here you can see that there is a little bit of a fluctuation actually. Okay, so the output voltage fluctuates because of the changes in the load. Okay, so something that you haven't seen before. The other case, the last case that we are going to look at is, instead of having perturbance on the load, let's see if our load jumps from 4 ohms to 4 plus 2, and then jump back to 6 minus 2, 4. So jump from 4 to 6 and then jump back to 4 ohms. All right, now let's take a look. All right. Technically, if our converter is ideal, we shouldn't see any changes in the output voltage, because the output voltage is independent under steady state conditions, independent of the value of the load. But unfortunately, you see a behavior like this, for instance. So my output voltage before was 12. After the transition is over, again goes back to 12, because under steady state conditions, load should not determine your output voltage, assuming that you're operating under continuous conduction mode. But during the transition, you can see the output voltage has a peak of almost 15 volts, Well, it depends on your load and depends on the other components connected there. Maybe 15 is too much. It's going to damage your load, for instance. So you basically have to come up with a solution to minimize this overshoot of almost 3 volts. When the load jumps back down, now we have an undershoot of almost the same magnitude. So 12 before, 12 after, but in between it actually dips into almost 9 volts. Again, 9 volts, for instance, it's a CPU, and if the voltage goes beyond a certain threshold, the CPU is going to shut down or something like that. So we have to mitigate these transitions. All right. So this was all about basically having the system in an open loop fashion. Now what I do is I start closing the loop. For instance, my first suggestion as a compensation network is a gain of 100. I'm just making the system a little bit sensitive to the difference between the output voltage and the reference, basically. So I'm selecting this here and here. And by the way, I'm actually using that threshold block over here as well, because practically you always have a threshold. You cannot, like, even if your compensation wants your duty cycle to be 7, but it can go from 0 to 5 in terms of the range that is accepted, or negative territories are not allowed. So I'm actually blocking this to go beyond 5 and below 0. All right. So right now my compensation network is just this gain of 100. And for instance, let's perturb the input voltage. Okay. The system is a little bit chaotic. You can see again the output voltage on average is 12. Okay. This average value is 12, but you can see there's a lot of noise and randomness going on in the system because we're just randomly, the system is too sensitive to the compensation network, and just randomly, things are happening. In parallel with these time domain calculations, I'm also looking at the Bode plus to be able to see if I can have a frequency domain description of or explanation of what is going on in the system. So here I have the exact same system. It's a buck converter. Input voltage 48, output voltage is supposed to be 12. Inductor is 220 micro, capacitor is 10 micro, load is 5, switching frequency is 75 kilohertz. And I mean all the math that we have already seen before, the resonating frequency, the corner frequency, the quality factor, duty cycle is 25%, VREF is 2.45, so H of S is this transfer function. My modulating block has a VM of 5, so I'm actually constructing all of these transfer functions, and this is the control to output transfer function of the buck topology. You have a crossover frequency that is slightly higher than 100,000 radians per second. The low frequency gain is about 35 dBs, which is between, let's say, about 70, for instance. It's actually good enough. In terms of phase, the system is stable. Hold on, let me make it a little bit smaller. Okay, this is my crossover frequency. In terms of gain, phase margin, I'm always positive. So buck converter is a very well-behaving converter. It's really hard to make it unstable because it doesn't have that right half plane 0. So I'm looking at audio susceptibility, which is the input or input voltage to output voltage transfer function. You can see that at lower frequency it has an attenuation because it's negative. That's the attenuation that decontributes the duty cycle 25%. Here is where I actually apply my compensation network. Now, if you are not familiar with let me just copy and paste. If you're not familiar with MathGAD, Okay, somehow it selects everything. If I have like GC, compensation network transfer function, defined up there and defined again, the last one is the one that matters. So the top one don't really matter. So I'm just trying to... So what we did first was, we just said this is 100, okay? Okay. So now I'm looking at the loop gain after this simple compensation network of 100, just the gain of 100. Okay. So because I have added some more gain to the system, my crossover frequency have moved to the right. Right now it's about 300,000 radians per second. The prediction is the system is supposed to be stable, but the phase margin is very, very small. It's like we are on the boundary of being stable and not being stable. That's why we see that chaotic behavior in the output voltage. The output voltage was very noisy. Now, you may say, okay, this compensation of 100 was not good. Let me, for instance, reduce it. Maybe 100 was too much. So let's reduce it to maybe, for instance, just 10, for instance. Well, we face an error, so let's forget about that. Let's go to the next step. Let's say I also, in order to eliminate the steady state error, I want to add an integration block to my loop. So now my new transfer function is 100 over S. Okay. Okay. Okay, you can see the system, like what we saw last time, as soon as you add an integration block into your loop, the system gets really sluggish. So it takes forever to reach the steady state. I still have almost the same amount of perturbation in my output voltage. Now remember, our input voltage is being perturbed from 48 to 48 plus 4 and 48 minus 4. And the exact same thing is actually appearing in the output voltage. So this just integration does not really help us. The reason is, if you look at the MathCAD file, okay. Okay. You can see that integration, because it actually moves your crossover frequency to the left. So your crossover frequency is very small, your bandwidth is small, therefore your system is sluggish. It's only 200 radians per second. The system is still stable. My phase margin is about 90 degrees. If you are curious about how come this line is jumping from here to here, this is a problem that MathCAD has. It cannot draw continuous phase angle. So it goes from negative 180 degrees all of a sudden to positive 180 degrees. But here I only have up to 45 degrees, so actually I don't see it. If you actually increase this to 180, you can actually see the rest of the graph. Okay, so what you got to keep in mind is this part of the graph should be drawn over here for my Bode plot to be accurate, but MathCAD doesn't really do a good job. So let's go back to 45. And we don't care about anything that is below 180 degrees anyway, because the system is going to be unstable, so we should be avoiding it anyway. So adding an integration block did not make the system unstable, this particular one. Sometimes it does actually. You just add an integration block and you get a lot of phase delay. And I'm also looking at my closed loop line to output transfer function. So what is this closed loop line to output transfer function? These are these transfer functions, this whole thing actually. Okay, GVG is the open loop line to output transfer function. Once I close the loop, there is a division by 1 plus t, and that's the closed loop line to output transfer function. Same note on the output impedance. The output impedance that we have is the open loop output impedance. Once you close the loop, there is a division by 1 plus t. So then that's the closed loop output impedance. All right. So I'm actually looking at them as well. You can see that adding an integration block, the red one is the open loop. The blue one is after you add an integration block. Now, remember, we want this transfer function to be as small as possible. Ideally, we would like it to be 0 or negative infinity dBs. So the more or closer that I am in these negative territories, the better it is. You can see this integration block for a little while does a good job, because if I continue this to the left, this blue curve gets more and more and more negative, which is very good actually. But my fluctuations in the input voltage is happening at 100 hertz, right? I was fluctuating my input voltage, or I was perturbing my input voltage at 100 hertz. Hold on. Okay, this is at 100 hertz. Now, if you look at the transfer function at 100 hertz, there is not a lot of extra attenuation. The blue curve, which is the transfer function after the loop is closed, it's almost the same as the red one, which is as if we don't even have a transfer function. We don't have a basically integration block. So you can see there is not a lot of attenuation that is happening here. So this is not good. In terms of output impedance, I did not perturb the load yet, but almost the same story. The contribution of the integration block is positive at very low frequencies or even DC frequencies, but beyond that, it is not that good. So one thing that may come to your mind is, what if I increase the gain? I had a gain of 100, then an integration block. What if I increase the gain? Because I already have a lot of phase margin going on, so I can actually afford increasing the gain. So let's increase the gain. Instead of being 100, let's make it 1,000. Let's make it 10 times more. All right. So I would expect my loop transfer function to jump to the right. So my crossover frequency is going to jump to the right. So it jumped to the right. So again, the bandwidth is better. System is faster. Is the system stable? Yes. This is my crossover frequency at this point. It's about 2,000 radians per second. And my phase margin is 90 degrees, almost 90 degrees, which is very good. At the same time, adding that gain of 10 puts this new line to output transfer function in more negative territories. So now if you see at 100 hertz, which is, by the way, 100, you have to convert 100 to radians per second. So it's about somewhere around here. I get some extra attenuation over here. That means now if I run the system with an extra gain of 10, assuming that it doesn't give me an error, okay. So let's look at before and after. This is still before. Look at the peak value of the output voltage. It goes as high as 13 volts. Okay. Now I increase the gain 10 times. I'm expecting that this would be reduced basically. So this extra peak. So it's only going to 12.3. So one trick could be just keep increasing the gain, and everything is going to be good. And you can also observe that the system got faster. It actually gets to the steady state quicker because the bandwidth is wider. So if increasing the gain is good, let me just keep increasing the gain. Let's, for instance, add another 10 times of gain over here. So instead of, or maybe let's go to an extreme of 100 times more. I'm going to add 2 more zeros. So we're looking at a DC, a gain of 100,000.
So is this gain the GC of S?
Is this gain what?
Is this the GC?
Yes, so now our GC is 100,000 over S, exactly. Okay? Okay, you can see that the system has gone unstable, okay? It's just all over the place. So let's look at our Bode plot and see if we were able to predict this behavior. So we got greedy. Instead of gain of 1,000, we chose a gain of 100,000, okay? Okay. So gain is higher. The whole Bode plot, in terms of the magnitude curve, is going up. So my crossover frequency now is about 50,000 radians per second. And if you see at 50,000 radians per second, this curve should go to the negative territory. So actually my phase margin is now negative, so the system is unstable. So that makes sense. However, the funny thing is, I'm doing a great job, assuming that the system was not unstable, I'm doing a great job attenuating the perturbations in the input voltage, because at this frequency that my input voltage is perturbed, you can see I have a huge amount of negative dBs. I'm attenuating it a lot, but the system is unstable to begin with, so there is no point in doing that. So just keeping increasing the gain may not be the solution. So now I can actually make my compensation network a little bit fancier. For instance, let's make it a little bit fancier. Let me just okay. So this is the fanciest that I have. I still don't want to make it that fancy, but let's say, for instance, 100 over S and 1 plus S over 100. Let me delete this. S 100,000. Okay, something like that. So why did I choose this? So I have still have the integration block. 1 over S is there. The gain of 100 is there. And I added a 0 at 100 radians per second. And I added a pole at 100,000 radians per second. So now you can see this is my new transfer function. So you can identify there is a 0 over here because my Bode plot basically breaks. Instead of keep going down with the slope of 40 dBs per decade, all of a sudden it comes back up. It gets flat. Then the rest of the system actually, the rest of the poles in the system kick in over here. The reason that you add a 0 over here is to actually add extra basically phase margin, because zeros give you positive phase angles. So your phase margin increases. Now let's take a look. My crossover frequency is somewhere around here, let's say 330,000 radians per second. And we are very close to being unstable, but just let's run it and see what the system looks like. In terms of attenuation, you can see that we are actually doing some attenuation. Let's go back to this. Well, I don't even, I think this is the one we just made. So let's just switch to this. Okay. So the system is not unstable anymore. I don't really see a significant improvement compared to the time that we only had like 100 over S or something like this. And this closed loop transfer function is predicting that we are not adding a lot of actually extra attenuation over here. So this becomes, your nightmare. Should I add more zeros, more poles? Where should I put them? How should I put them? What is going to be my gain and things like that? So what I'm going to do now is I'm going to kind of introduce a an approach in terms of what our transfer function should look like. We gotta use this Bode plots to fine-tune our final design. And then if it works here, it doesn't mean that it's gonna work for the rest of your lives. This is just for you to give a sample. Like if you are designing the boost converter, because of the right half plane 0, it might actually be a little bit more complicated or something like that. So we tried a few candidates for our actually compensation network. Let me show you the best candidate that we have, which is this fancier one. The one down here, you can see it's a little bit more complicated. It still has that 1 over s kind of transfer function, an extra 0, an extra pole, an extra 0, an extra pole. So we have 2 zeros and basically 3 poles in our transfer function. And now I'm actually perturbing my input voltage. So I'm still perturbing the input voltage. Okay, now you can see that I'm back to a very good case. Even though my input voltage is going from 48 to 48 plus 4 and minus 4, my output voltage doesn't change much. It's actually relatively around 12. I mean, obviously there is a little bit of a ripple on it, but it is not that significant. So an indication that that transfer function was a good candidate. So the question is, how can we get to that good candidate, or how can we design that transfer function? So this is what I'm going to talk about now. Any questions? All right, so these files are on Blackboard. I would encourage you guys to go there and play with it a little bit. Sometimes I actually gave a homework assignment about these 2 files. You know, go and put a gain of 100 and make an observation, then a gain of 200 and make an observation. I don't know, I might do that for your next homework assignment. I'm not quite sure. Okay. So we got to talk about loop gain design procedure. Okay, let me make it red.
So all the GC, GM, and HS would lie in the feedback path?
Yes, they were all in my mathget file. They were all actually being multiplied. Let me show it to you. So when I was looking at my loop gain, I was actually multiplying all those gain. Here's my loop gain. H is here, compensation is here, modulation block is here, and the control to output voltage transfer function of my buck converter. They're all there. All right. But we can only design G sub C. The rest of them are pretty much constant or given. So the best, or arguably the best, compensation network would look like this. We have a gain that we can adjust, go up and down. We have a division by S, which is the integration block to eliminate the steady state error. Then we have 2 zeros and 2 poles. Okay. So we have 2 zeros, omega Z1, omega Z2, and 2 poles, omega P1 and omega P2. So remember, this transfer function has to be causal in a sense that the number of zeros in any natural transfer function, if it's something that you can physically implement, should be less than the number of poles. Here we have 2 zeros and 3 poles, no problem, everything is going to be fine. Okay? All right. So the whole question is, what should I select for my omega Z1, omega Z2, omega P1, omega P2, and also the gain of A? Okay. All right. So step 1. So we are going through like a step-by-step procedure. Okay. Before getting to the controller, you got to make sure your power stage is well designed. The person who has designed or sized the capacitor and the inductor has done a good job. And so like the ripple in the output voltage is less than 1%, you know, those kind of things. We are operating under continuous conduction mode and things like that. If this happens, you are guaranteed that omega naught is at least 10 times smaller than omega s. Omega s is the switching frequency. Okay, whatever your switching frequency is, like 100 kilohertz, or in my example 75 kilohertz, just multiply by 2 sub pi, and that's going to be your angular switching frequency. Actually, let me add it, angular. Omega naught is the corner frequency. So whatever the transfer function is, if you remember in the canonical form, there is an omega naught appearing over here. For instance, for the Bach converter, omega naught is 1 over the square root of L times C. Okay? All right. By the way, if you plot, let me just mention it here, this compensation network, if you really plot the Bode plot for that, I have this integration block first. So I have a gain of negative 20 dBs per decade. Then I hit omega Z1. So it gets flat. Then I hit another 0. Usually the zeros are low frequency zeros. So it starts actually increasing with a gain with a slope of 20 dBs per decade. Then I hit omega P1, so it gets flat again. Then I hit omega P2. And this is just GC. Okay. So this is where we are looking at low frequency zeros and high frequency poles. Yes?
How we compute the order of appearing the zero and poles?
Usually you put the zeros at lower frequencies to get a phase boost, and then you put the, and we're going to talk about it, you put the poles at higher frequencies to get extra attenuation at higher frequencies. Okay, something like that. Otherwise, there is no point. Okay, so as first step, double check your power stage. Make sure your corner frequency is at least 10 times smaller than the switching frequency. Yes?
When we make corner frequency very less than the switching frequency, will that not make our controller a very slow one?
It would make our converter very slow. That's a good point. But if you try to make your converter fast by pushing your corner frequency to higher frequencies, you are going to observe a lot of ripple in your output voltage. Okay, so there's a trade-off between a smaller ripple and basically higher corner frequency. Very good point. So yeah, you can, I don't have a simulation here, but you can run it and make them close to each other. So this whole corner frequency means your converter is doing a good job filtering the switching frequency harmonics. If they are not, if they are close to each other, omega naught and omega s, then you are not doing a good job filtering them. So all of the switching frequency appears in your output voltage. So you have a lot of ripple. So to graphically describe this, let me show you what I mean. Let me see. For instance, in this graph, G sub VD, I mean corner frequency. All right, let me show it over here. I'm looking at the output side of my converter that I have an inductor of L and a resistor of R placed in parallel with the capacitor of C, like an impedance network. Okay, to answer that question, you can see my corner frequency somewhere around here. Okay, wherever I have this peak. My switching frequency is actually way up here. So I'm running, for instance, the system at 75 kilohertz, then 75 multiplied by 2 multiplied by pi. We are looking at about 1,000,000 radians per second. So it's somewhere around here. And you can see at this particular, if I continue this to hit my, my switching frequency, you can see you're getting a lot of attenuation. And that's good. That's why you were doing this. Remember, you're looking at a low-pass filter that should attenuate the harmonics of the switching frequency, and you're doing a good job. If they get too close to each other, then you're only attenuating by this much, which is not enough. So you're going to have a lot of ripple. Okay. So that was all about the power stage. So just make sure your power stage is well designed. So if you follow that procedure of, remember those equations, L should be greater than D over R over whatever, or C should be greater than this. If you follow those procedures, this requirement is already satisfied. All right. Step 2 is actually talking about your zeros. Okay. Okay. Whatever your omega naught is, your omega z's should not be very far from it, basically. And how small or how large should they be? It becomes basically a trade-off between bandwidth and phase margin. Okay, on one side, if you increase them too much or reduce them so much, the bandwidth is going to grow, but the phase margin is going to shrink, and vice versa. So a good place would be placing them somewhere around here. Whatever your corner frequency is, between the corner frequency or twice the corner frequency down to 10 times smaller than the corner frequency. That's usually, typically a good place to place your zeros. So this gives you a rough idea where omega z1 and omega z2 should be. By the way, omega z1 and z2 should be could be identical, not necessarily though. Then place, what about omega p1, the poles, omega p2, place them around the switching frequency. If they are too small, your bandwidth is going to suffer. If they are too large, they don't really have a good impact in terms of eliminating the switching harmonics and high frequency noise attenuation.
Excuse me.
Okay, so a good place, a roughly good place would be place them greater than 10 times the switching frequency. Wait a minute, 10 times, yeah, and the switching frequency. So there should be larger than the switching frequency, but not more than 10 times larger. Otherwise, they are not going to have much of an impact. All right, we're running out of time. I'm going to continue this design procedure, and I'm going to just go back to that Bode plot and show you what things look like, and then come back to the simulation file and basically run it one more time with the good compensation network. All right? Yes?